Have you ever, like, stopped and really thought about the everyday things around you? Your coffee mug, maybe a candle? How much do we actually know about what they're made of?
It seems simple, right? But underneath, there's often this incredible complexity, a really rich history, even some clever design. So today, we're going to really dig into two of these fundamental material families, ceramics and waxes. We've got this great document to guide us, kind of giving us a unique look into them, from way back in ancient times, their basic properties, right up to how we use them today, even the economics behind making them. Our mission really is to pull out the most important bits, the surprising facts, and just help you get a solid handle on these materials quickly. We're going to unpack all of that.
Yeah, and that's what makes this so interesting, I think. It's amazing how these materials are just, well, everywhere in our lives. We often don't even notice them, but their journey through history and the science behind them is just, it's pretty extraordinary. Okay, so let's start right at the beginning. Definitions. When we say ceramics, what are we actually talking about? Our source gives a really clear starting point here. It says there are a wide range of inorganic, non-metallic articles. Okay, so inorganic, non-metallic. That tells us a couple of things straight off. They don't come from living things, and they're definitely not metals. That kind of sets them apart already.
Right.
But what really makes them stand out, why they're used for things that need to last, are those key features. They're fire resistant and corrosion resistant. I mean, think about that. Stuff that can handle intense heat and doesn't break down easily with chemicals, that's a powerful combo.
That really is.
And how they're made, it sounds almost, simple. Usually heating up a mix of clay, water, and sometimes other stuff like sand, feldspar, temper, basically earth and water, right? Add fire and you get something super tough. It's like ancient alchemy almost.
It really is kind of like alchemy. And what's fascinating here, especially when you put it next to ceramics, is how different waxes are chemically. You mentioned ceramics are inorganic, generally no carbon-hydrogen bonds derived from minerals, that sort of thing. Waxes, on the other hand, are fundamentally organic compounds.
Oh, okay. Big difference.
Huge difference. And it dictates pretty much everything about how they behave. Their basic structure is mostly these long chains of hydrocarbons molecules made almost entirely, hydrogen and carbon. And just like ceramics come from natural stuff like clay, waxes also have natural sources. Animals make them, think beeswax, or they can even be found in minerals, like certain types of petroleum waxes.
Very beeswax.
But then there's this whole other category, a growing one too, of synthetic waxes, man-made ones, basically, engineered for specific jobs. And physically, they're usually solid or maybe semi-solid at room temperature. But, and this is key, they have a pretty low melting point. Heat them up a bit, and they turn liquid. So that fundamental difference in their molecules, inorganic, needing intense heat to transform, versus organic, relatively easy to melt. That's really the core reason they have such different properties and, why we use them for such vastly different things.
Yeah.
It really drills down to the chemistry right at the molecular level.
It's amazing, isn't it? Just those basic definitions kind of point you in completely different directions for how they're used. Like, yeah, two sides of a coin chemically, but both totally essential in their own ways. Speaking of essential, the story of ceramics is, it's practically woven into the start of human civilization itself. And here's where it gets really interesting, maybe a bit unexpected. The source says the very first ceramics we know of weren't like pots for food.
Right. You'd think storage, maybe cooking.
Exactly. But no, they were figurines, little statues. And they date back to, get this, around 29,000 BCE. Found in Europe.
Wow, 29,000 BCE. That's incredibly early.
It's mind-blowing. Way before farming took hold, before people really needed permanent storage. Humans were already taking clay, using fire, and making art. It wasn't just about survival, was it? It was about, expression, maybe ritual. It just shows that urge to create, to shape things, is super deep in us. And ceramics were one of the first ways we did it.
And if you connect that to the bigger picture, how societies evolved, it really shows how technology and materials kind of grow together with our needs. So, okay, those early figurines were maybe art or ritual. But then the source points out this huge shift when agriculture started and people began settling down.
Right, the Neolithic Revolution.
Exactly. That period, roughly 6,000 BCE up to maybe 1600 CE, that's when pottery really became, essential, a critical tool.
Yeah.
It's a classic case of necessity driving invention, isn't it?
Yeah.
Once you're growing crops, suddenly you need to store the harvest, keep pests out, maybe move it around. You need containers that can handle cooking heat and containers that won't, spoil the food. So pottery gave them that. Durable, heat resistant, relatively waterproof containers. It literally helped people put down roots and build communities.
And the story doesn't stop there, does it? The source highlights how from around 1600 CE onwards, when global trade routes really started opening up, it wasn't just about spices and silk. It massively influenced how ceramic techniques and styles spread across the world.
Yeah.
Like imagine potters in Europe seeing this incredibly fine, delicate porcelain coming from China during the Ming Dynasty. They'd be blown away, right? And they tried desperately to figure out how to make it themselves, which eventually led to breakthroughs like bone china in England.
Right, that drive to replicate and innovate.
Yeah. Or think about new glazes, different ways of firing the clay, traveling along trade routes like the Silk Road, mixing and matching across cultures. It became this truly global exchange of ideas and technology. That's a real aha moment for me, realizing how interconnected things were, even affecting something like pottery design. It shows how trade and just human curiosity push innovation forward.
And the story of wax, it's just as long and deeply connected with what humans do, even if maybe it's less about, the big structures of early cities. Our source points out that even before 500 BCE, people were definitely using waxes on purpose.
Okay.
In China, for instance, we see records of beeswax candles way back in the Tang Dynasty. That's like 616 to 907 AD. So early innovation in lighting over there. And then you look at, say, the ancient Egyptians and Romans, different part of the world, and they were heavily reliant on tallow, basically animal fat for light. It really highlights this universal need, doesn't it, to push back the darkness, to do things after sunset.
Yeah, absolutely. And it became much more than just, seeing where you're going. Between roughly 500 BCE and the 1800s, you see cultures all over the place developing really clever ways to make candles from all sorts of natural waxes. Beeswax, obviously, but also waxes from insects.
Insect waxes, like what?
Yeah, like from the Chinese scale insect, apparently. And loads of plant-based waxes, too, like bayberry wax or carnival wax from palm leaves. And these weren't just functional, the source makes a point of this. They played huge roles in religious ceremonies, lighting sacred spaces.
Ritual significance.
Exactly. And just in everyday life, too, lighting up homes and streets. Lighting a candle wasn't just practical. It had real cultural weight in so many different places.
And wax was used for so much more than just light, especially if you move into the Middle Ages and beyond. The source mentions some really neat historical uses, like sealing wax, absolutely vital in the Middle Ages for making sure documents were authentic and hadn't been tampered with. It was like an official stamp and security measure all in one.
Ah, the wax seals on old letters and documents.
Precisely. And even earlier, in ancient times, they used wax tablets. You could write on them and then smooth the wax over to reuse it. Super versatile even back then for recording things.
Yeah.
But a real turning point, a huge one for the wax world, came in the 1850s. That's when paraffin wax was introduced.
Right, the petroleum stuff.
Exactly, a byproduct of refining oil. And it was a total game changer. It burned much cleaner than tallow, and crucially, it was way, way cheaper than beeswax or animal fats.
So better light for more people.
Absolutely. It really democratized artificial light, made it affordable for almost everyone. And fast forward to today, the uses for wax are just immense. It's not just candles anymore. It's a key ingredient in countless cosmetics, lipsticks, creams giving them structure and smoothness. It's in food products, like coatings on cheese or in chewing gum. And tons of industrial processes use it. Polishes, lubricants, casting molds. That simple process of refining crude oil gave us a material that totally changed home life and industry.
It really is kind of mind-boggling to think that, some bee byproduct or animal fat first used for just a tiny flame evolves into this petroleum derivative that's crucial for cosmetics, food industry. It's such a long, winding history between humans and these seemingly basic materials. Makes you wonder what's next for them,
Yeah, it's a great example of how we keep finding new ways to use the resources around us.
Okay, so we know what they are, roughly, and we've seen their incredible history. Now let's get into the nitty-gritty, the science bit. What actually gives ceramics and waxes their unique characteristics? Why do they behave the way they do?
Right. For ceramics, their main properties tend to be pretty, robust, often reflecting how they're made or used, usually involving high temperatures. Our source lists several key traits. First, they're known for exceptional hardness and wear resistance.
Meaning they don't scratch or wear down easily.
Exactly. They can handle a lot of friction and abrasion. Then there's their impressive heat resistance. They perform really well at very high temperatures.
Okay, I think makes sense for ovens and things.
Definitely. They also have strong chemical resistance, meaning they don't react easily with many corrosive substances. Then there's their characteristic brittleness. They tend to fracture or shatter rather than bending or deforming under stress.
Yeah, I've all dropped a mug.
We have. And finally, they have specific electrical and thermal properties. These can actually vary quite a bit depending on the exact type of ceramic, ranging from being great insulators to sometimes even conductors. And maybe we can elaborate a bit on why these matter so much. That hardness and wear resistance, that's precisely why ceramic tiles last for ages on floors, even with people walking on them constantly, or why ceramic parts are used in engines or machinery where things are always rubbing together. Heat resistance, absolutely vital. Think furnace linings, those heat shield tiles on spacecraft re-entering the atmosphere.
Wow, yeah.
Or even just the glaze on your casserole dish. Chemical resistance makes them perfect for lab equipment, storing harsh chemicals, or even things like medical implants where you need something totally inert. Now that brittleness.
It sounds like a downside, right? And it can be. But it raises an important question for engineers. How do you work around it? Well, they design shapes that spread out stress better, or they make composites mixing ceramics with tougher materials, or they use special glazes or treatments to make the surface stronger. So it's a challenge, but one that material scientists know how to manage.
So you design with the brittleness in mind, almost. Exactly. And their electrical properties are super useful too. Most are excellent insulators. Think spark plugs or those big things on power lines, stopping electricity from leaking.
Yeah.
But some advanced ceramics can actually be semiconductors or even superconductors for high-tech electronics. And thermally, they're often poor conductors of heat. That's why your ceramic coffee mug doesn't instantly burn your hand, even with boiling coffee inside. Great thermal insulators.
Yeah.
So all these properties together dictate why ceramics get picked for such a huge range of demanding jobs.
It's incredible how those basic traits lead to such diverse uses. Okay, so now let's switch over to waxes. Our source lists a very different set of characteristics, almost the opposite in some ways.
Right. Typically, waxes are described as soft and solid at room temperature, having a relatively low melting point, being insoluble in water.
Meaning water doesn't dissolve them.
Correct. But they're generally soluble in organic solvents. And of course, they are flammable.
Just thinking about that list. Wow, the contrast with ceramics is stark. Hard, heat-resistant, stable ceramics versus soft, melty, flammable waxes. But both incredibly useful just for totally different things. It really shows the breadth of material science.
Absolutely.
And you can see how those properties play out in everyday life, can't you? Why does a candle melt nicely? Low melting point, controlled flammability. Why can't you just wash wax off your hands with water? Insoluble in water, which also makes wax great for waterproofing things.
Good point.
And why can you spread shoe polish or car wax into a smooth layer? Because it's soft enough and soluble in the right carriers to make an even coating. It really does all come down to those fundamental characteristics driving how we use them. Okay, this is where ceramics get really fascinating because it's not just one thing called ceramic, it's a huge family. Our source breaks it down into two main broad categories, traditional ceramics and advanced ceramics. Understanding that difference is pretty key, apparently.
It really is.
Yeah.
And what's fascinating here is the leap it represents, going from working with natural materials, which could be a bit unpredictable, to materials that are precisely engineered. It's a shift from discovery to deliberate design, really.
Okay.
So traditional ceramics, these are mostly made from natural raw materials, things like feldspar, quartz, and especially different kinds of clay. Their final structure, things like how porous they are, how strong they are, depends a lot on the specific minerals and, well, impurities in the clay they started with.
So more variation naturally.
Exactly. Often a more imperfect structure compared to advanced ceramics. And they're usually made using fairly straightforward methods, like wet molding. You find them mainly in everyday items and building materials, think bricks, roof tiles, basic pottery, the workhorses, you could say.
Right, the stuff we see all around us.
Then you have advanced ceramics. These are a whole different ballgame. They represent a huge step forward in material science. They're not just found in nature. They're meticulously designed and engineered using synthetic, very high purity powders. Things like aluminum oxide, silicon carbide, silicon nitride.
So starting materials are man-made and pure.
Precisely. And they're manufactured with a specific goal, to have highly tailored properties for really demanding high-performance uses. The manufacturing involves specialized techniques, high-temperature sintering, hot pressing, things like that, to control their internal structure very precisely. And this control gives them unique properties. Incredible strength, much better toughness than traditional ceramics, amazing wear resistance, stability at extremely high temperatures, and often they're very chemically inert. They can be engineered for specific jobs too, like being permeable, magnetic, insulating, or even conductive. It's really about creating the perfect material for the job.
That distinction makes so much sense. It shows that evolution from just using what's there to actually designing materials for specific needs. Okay, so let's dive deeper into some of these advanced ceramics the source mentions. They sound pretty specialized. First one listed is silica. That's SiO2, right? Silicon dioxide. The source highlights its amazing thermal shock resistance, meaning it can handle rapid temperature changes without cracking, and low leachability, meaning stuff doesn't easily dissolve out of it.
Both very important properties in demanding environments.
Definitely. It says these made it super valuable in aerospace and energy sectors. Specifically, it's used for making investment casting shells and cores.
Ah, okay. Those are used to make really precise metal parts, often with complex shapes, for things like jet engines or turbines. The silica mold needs to withstand the molten metal's heat and then be easily removed without reacting with the metal or cracking from the heat difference.
Right, so stability is key there. Okay, next up, fire bricks. The name's a bit of a giveaway.
Pretty descriptive, yeah. These are made from refractory materials, basically stuff that holds its strength at really high temperatures.
Yeah.
Usually a mix of special clays and other heat-resistant things like alumina or silica.
And their job?
Their main job is to line the inside of high-temperature furnaces, fireboxes, kilns, basically anything that gets incredibly hot. They act as a protective barrier. The crucial thing is they can handle extreme heat, often over 1,000 degrees Celsius, for long periods without falling apart.
Wow.
Plus, they usually have low thermal conductivity. That's important for energy efficiency. You don't want all the heat leaking out of your furnace, so you find them everywhere in heavy industry, steel making, glass making, even in the kilns used to make other ceramic products. They're kind of the unsung heroes enabling all that high-temperature manufacturing.
Makes sense. Okay, moving to something maybe a bit more elegant. Bone china. That we usually think of fancy teacups, right?
We do, yeah. And it is often called fine china. But it's more than just pretty. The source points out it's known for being surprisingly strong, resistant to chipping, and having that distinctive translucency, that sort of see-through quality.
And the bone part is literal.
It is. The unique recipe includes bone ash, usually from cattle bones, mixed with kaolin clay and feldspathic material. It was pioneered by an English potter, Josiah Spode, back in the 1800s. He was aiming for something better than standard porcelain.
And he found it.
Seems so. What's amazing is that it's actually more durable than regular porcelain in some ways, which allows it to be made much thinner and more delicate looking while still being tough. And that translucency, that warm white glow, doesn't come from melting like glass, vitrification. It comes from the specific way the minerals, especially the bone ash, react during firing. So yeah, used for fancy dinnerware, decorative items, beautiful and surprisingly resilient.
That's fascinating about the thinness and durability. Okay, one more advanced type here. Glass ceramics. Sounds like a hybrid.
It kind of is. They're composite materials. Imagine tiny, precisely controlled crystals growing within a glassy, non-crystalline matrix. They're made in a two-step process. Melt a specific glass recipe, cool it quickly, then carefully heat it again, called ceramming, to make those crystals form inside the glass.
And why do that? What's the benefit?
That careful mix of glassy and crystalline parts gives them a fantastic combination of properties. High strength, good toughness, resisting cracks, and excellent thermal shock resistance. They can handle sudden temperature changes really well.
Where did they first get used?
You might be surprised. Originally, they were developed for mirrors and mounting structures in astronomical telescopes, places where you need extreme stability even if the temperature fluctuates.
No way. Telescope mirrors.
Yep. But today, they're everywhere. Think about those smooth, black ceramic cooktops on stoves that's often glass ceramic. It handles the heat, the occasional drop pot.
Ah, okay. I always wondered what that stuff was.
Exactly. Also used in tough cookware, bakeware, even in high-performance reflectors, inside digital projectors. It's a great example of a super specialized material finding its way into tons of everyday applications, often right in our kitchens.
That really is incredible. The journey from telescope mirrors to my stovetop. Advanced ceramics are clearly playing these huge, often hidden roles everywhere. Okay, let's shift now to the ceramics we might handle more often, the pottery ceramics. The source breaks this down into three main types.
Right, the ones we often think of when we hear pottery. First is porcelain. We touched on it a bit with bone china, but standard porcelain is huge too. It's primarily made from kaolin clay, a very pure, fine white clay that's great to work with, very malleable.
And it looks...
usually white, sometimes translucent, known for being hard, strong, and durable.
Mm.
The key is the firing. It's fired really hot, 1200 to 1450 Celsius. This intense heat vitrifies it.
Petrifies, makes it glass-like.
Essentially, yes. The components melt and fuse, making it super dense, strong, and totally non-porous, impermeable to water. So yes, used for beautiful decorative art and fine dinnerware, but because it's strong, non-porous, and a good electrical insulator, it's also used for things like electrical insulators on power lines, or even high-tech stuff like dental implants. It really blends beauty and function.
Okay, porcelain. Then there's stoneware.
Stoneware. The source describes this as strong, durable, and really resistant to chipping and scratching. It's kind of the everyday workhorse for practical stuff. Dinnerware that gets used daily, bakeware, general pottery.
Also high-fired.
Yes, fired at high temperatures, typically a bit lower than porcelain, maybe 1200, 1300 Celsius, but still hot enough to vitrify the clay, making it dense, hard, and non-porous. That high firing is what gives stoneware its strength and durability. It's built to last.
Right. And the third one is earthenware.
Earthenware. This is often used for more decorative pottery, vases, figurines, that kind of thing, but also for practical items like flower pots, because it is porous, and sometimes rustic cookware. The key difference is the firing temperature. It's fired much lower than stoneware or porcelain.
And that makes it
Porous, meaning if it's not glazed, it will soak up water, so it's generally less durable. But that porosity also makes it great for decorating. You can glaze it to make it waterproof and stronger, or leave it unglazed for that natural, earthy look. It's often decorated with colored slips, paints under the glaze, lots of possibilities. Think terracotta pots. It's a classic earthenware. It has a unique, often rustic charm.
So what does this all mean for, us when we're buying stuff?
Well, it means understanding that firing temperature and the clay type really dictate the properties. Is it going to be delicate and translucent like porcelain, sturdy and chip-proof like stoneware, or porous and maybe more decorative like earthenware? Knowing the difference helps you choose the right thing for the right job, whether it's dishes, a vase, or a pot for your plant.
That's super helpful. But wait, the source lists even more types. It goes beyond those main three, listing specific historical or regional styles. It's like a pottery world tour. Okay, so it mentions terracotta again, defining it as earthenware, low-fired, often reddish-brown. Then stoneware and porcelain are revisited to clarify their relationship. Stoneware is fired hotter than terracotta, denser, more durable. And porcelain is a specific type of high-fired stoneware using kaolin clay, giving it the white, translucent look.
Right, reinforcing those core distinctions. And then it gets into some really specific, often named types, like Delftware and faience. These are types of tin-glazed earthenware.
Tin glaze.
Yeah, the glaze uses tin oxide to make it opaque white. Delftware is Dutch. Faience, often French or Italian. They're famous for those blue and white decorations, often trying to imitate expensive Chinese porcelain back in the day.
Okay. I've seen that style.
Then there's Majolica, also tin-glazed earthenware, mainly from Italy and Spain. But Majolica is known for really vibrant, rich, multicolored designs, often depicting scenes or patterns, very popular during the Renaissance.
Colorful stuff.
Then Jasperware. That's that iconic Wedgwood style. It's actually a type of unglazed stoneware, famous for its matte colors, especially that pale Wedgwood blue, but also green, black with white classical figures in relief. Instantly recognizable.
Oh, yeah, definitely.
And speaking of Wedgwood, the source lists it specifically, noting it as a type of creamware, known for Jasperware, but also their black basalt bodies and other cream-colored ceramics. Finally, Staffordshire pottery. This refers generally to earthenware made in the Staffordshire region of England, which was a massive pottery hub, often decorated with transfer-printed designs, a way to mass-produce patterns, making decorative plates and things more affordable.
Wow. It's incredible how each of these has its own history, its own look, tied to a specific place or time. They're not just pots, they're like little pieces of history, aren't they?
Exactly. They carry centuries of craft, trade, and culture within them.
Okay, let's switch gears completely now. From hard-fired ceramics to the softer world of waxes. And just like ceramics, wax isn't just one single thing. Our source points out 3 main types we're likely to run into.
That's right. The first one, and probably the most common one you'll find, especially in candles, is paraffin wax. This is derived from petroleum.
So oil-based.
Correct. It's a byproduct of the oil refining process. Because it's readily available and relatively cheap, it's become the go-to wax for mass-produced candles. Because it's a pretty consistent burn, it's the industry standard, really.
Okay, paraffin. What's next?
Next is beeswax. Totally different origin story here.
Yeah.
This is a natural wax produced directly by honeybees inside their hives.
Ah, the classic.
Exactly. And it's really prized, not just for its natural sort of subtle honey scent and nice golden color, but also for its quality. Beeswax candles tend to burn longer and cleaner, often with less dripping or soot compared to paraffin. So it's seen as a more premium option used in higher-end candles, some cosmetics, even food-safe applications. People value its natural origin.
Right. And the third type?
The third major one highlighted is soy wax. This is a great example of a vegetable wax. It's made from soybean oil specifically, hydrogenated soybean oil.
So plant-based, renewable.
Exactly. And it's become really popular quite quickly. It's seen as a major alternative to paraffin, especially for people looking for more natural, sustainable, or biodegradable options. Soy wax generally burns cleanly too, and it's known for having good scent throw.
Scent throw.
Yeah, I mean, it releases the fragrance added to the candle really effectively. So it's become a big favorite for making scented candles. Its popularity really taps into that growing consumer desire for more eco-friendly products.
That makes a lot of sense. And you definitely see that reflected on store shelves, don't you? You see candles advertised as soy wax or beeswax, often positioned as better or cleaner alternatives. It's interesting that these choices really come down to those subtle chemical differences we talked about earlier. Like, even if we don't notice it directly, the source doesn't go deep here, but things like the melting point differ. Soy wax usually melts cooler than paraffin, which can affect burn time and how the scent comes off. Beeswax often melts even higher, making for a harder, slower burning candle. These little differences have big impacts on performance, cost, environmental footprint, and ultimately, what we choose to buy. Okay, so we know what they are, the different types.
Yeah.
Let's bring it right back home. Where do we actually use these things? Because honestly, ceramics and waxes are they're everywhere, built into almost everything we do. Let's start with ceramics again. The source lists a range that's almost hard to grasp. It's so broad. I mean, starting with the absolute basics in our homes. Pottery. Your dishes, plates, cups, mugs, vases. Fundamental stuff.
Things we handle every single day.
Exactly. Then think about the structure of our homes. Tiles on the floors, walls, kitchen counters, providing durability but also design. Even the bricks used to build the walls, the literal foundation of buildings, that's ceramic technology.
Yeah.
And sanitary ware, sinks, toilets, bathtubs, absolutely essential for modern living. And they're all ceramic fixtures. They really form the backbone of our homes, but it goes way beyond the house, right? Ceramics are critical as electrical insulators. Think about spark plugs making your car engine run, or those big ceramic things on power lines that keep the electricity safely contained while it travels to us. Huge safety role there.
Absolutely crucial.
And then at the really extreme end, heat-resistant materials. We mentioned the heat shields on spacecraft protecting them during re-entry. That's ceramics. The linings of industrial furnaces making steel or glass. Ceramics again. So what does this all mean? It means ceramics are literally holding up our homes, powering our grids, enabling transport, even letting us explore space. They're the quiet, tough materials making so much possible.
They really are. And waxes, while maybe less structurally obvious than a brick wall, are just as widespread, just in different ways. The source naturally starts with the most obvious one, candles.
Yep. Light, decoration, scent.
Yeah. Exactly. Still a key function for light, but hugely important now for atmosphere, decoration, delivering fragrance. That simple act of lighting a candle is almost universal, but their use goes way beyond that. Think cosmetics. Waxes are absolutely fundamental there. They give lipstick its shape and smooth glide. They act as emollients in creams and lotions, helping moisturize and create that protective barrier on the skin.
Ah, okay, so that's why lotions feel smooth and protective.
That's often the wax component doing that work. And the polishes. Furniture polish, shoe polish, car polish. The wax is the key ingredient, creating that glossy, protective layer that repels water and dirt and makes things look good. And beyond those, waxes pop up everywhere. Waterproofing fabrics, helping release things from molds in industry, making dental impressions, coating fruits or cheeses to make them last longer. Those properties we talked about, soft, low melting point, water insoluble, film forming, make them perfect for this incredible variety of jobs. Whether it's making your living room smell nice, keeping your skin soft, protecting your car's paint, or even helping preserve food, they're kind of the hidden helpers, making life smoother and more comfortable.
All right, we've covered the science, the history, the uses. Now let's get practical. Let's talk business, the dollars and cents, or maybe pesos in our example. How do manufacturers figure out how much ceramic or wax they actually need for something? And crucially, what's it going to cost them? This is where the lab meets the factory floor.
Yeah, it's where theory hits reality. The source explains that estimating how much material you'll consume comes down to three main things. First, Obviously, the size and shape of the final product. Bigger things need more stuff. Second, the thickness of the material that determines the volume. And third, something really important that's easy to forget: waste.
Waste, like leftover bits.
Exactly. Cuttings, trimmings, pieces that break or don't meet quality standards. No process is 100% efficient, so you always need to account for some material loss. And when you estimate the cost, four main factors usually drive it: the specific type of material you choose, how much of it you need, including that waste, the cost of labor to actually make the thing, and finally, transportation costs for moving materials and finished goods around.
Okay, that makes sense. Inputs for the budget. And our source gives a really great concrete example to illustrate this. Figuring out the cost of a standard ceramic mug. Something we all use, but probably never think about in this much detail. Let's walk through their calculation. So the scenario is a simple cylindrical mug, height 10 centimeters, diameter 8 centimeters, wall thickness 4 millimeters. And importantly, they're factoring in 10% extra material for that waste we just talked about.
Okay, let's follow the steps in the source. Step 1, calculate the lateral surface area. Now, the source uses a formula: 2 times pi times height times diameter. For our mug, that's roughly 3.14, 10 centimeters, 8 centimeters, which gives about 502.4 square centimeters.
Okay. Using diameter there is a bit unusual for a cylinder's side area, isn't it? Usually it's radius.
It is. The standard formula is 2 pi radius height. Using diameter doubles it. The source might be using a specific industry convention here, perhaps estimating the area of flat clay needed before forming, or implicitly accounting for inner and outer surfaces somehow. We'll stick with our number for this example: 502.4 centimeters or so.
All right, using the sources method. Step 1, 502.4 centimeters scale. What's step 2?
Step 2 is the area of the mug's base. That's just a circle. Pi times radius squared. The radius is half the diameter, so 4 centimeters. So 3.14, 4 centimeters gives about 50.24 centimeters. Simple enough.
Okay, base area, 50.24 centimeters. Step 3.
Step 3, again following the source's unique approach, says to multiply that lateral surface area from step 1 by 2 to account for top and bottom sides. So 502.4 centimeters times 2 equals about 54.8 centimeters in rods.
Multiplying the side area by 2.
Okay.
Maybe thinking about the total surface inside and out.
Possibly. Or maybe it's a simplification for the total clay body area. Step 4 is then to add the base area to that doubled lateral figure. So 1,004.8 centimeters per centimeters plus 50.24 centimeters ones gives a total of approximately 155.04 centimeters ones. That's the theoretical surface area of clay needed for one mug, according to this method.
Got it. And now we need to account for the waste.
Right. Step 5, factor in that 10% waste. We take the 155.04 centimeters one and multiply by 1.1. That gives us about 1160.54 centimeters ones. This is the effective starting area of material we need, including the expected losses.
Okay. 1,160.54 square centimeters of material needed per mug. Now, how much does that cost? The source uses an example price. Mid-range stoneware clay, locally produced in the Philippines, at 20 per kilo, Philippine pesos.
Right. Now, we need to get from our area, CM wrote, to a weight, Kitakabi, to use that price. First, volume. We multiply our area by the thickness, so 1,160.54 centimeters times 0.4 centimeters, which is 4 millimeters, gives a volume of about 464.22 cubic centimeters.
Okay, volume. How do we get to weight? Need density, right?
You do. The source simplifies this step, but effectively converts that volume to about 0.464 kilograms of clay. So just under half a kilo per mug, considering the waste and thickness.
All right, nearly half a kilo. So the material cost is 20 per kilo times 0.464 kilos, which is about 9.28, just for the clay.
Just for the raw clay, yes. Next is labor.
Labor, shaping, firing, finishing. The source says this can vary, but for a simple mug in the Philippines, maybe 10 to 20, they use an average estimate of 15 per rug.
Okay, 15 for labor.
And the last piece is transportation. Depends on distance, obviously. But assuming it's within the same region, the source estimates 1 to 5 per mug. They use an average of 3 ware for the calculation.
Right, so let's add it up.
Okay. 9.28 for the clay, plus US 15 for the labor, plus 0.2 for transport. That comes to 27.28 per mug. Total estimated cost. Wow. Okay, that is genuinely an aha moment. Less than 30 pesos, which might sound cheap, but breaking it down, you see the raw material cost, the significant chunk that's labor, the waste factor, the transport. When you just buy a mug, you never think about all those individual components adding up. It really shows the hidden complexity and economics behind even a simple, everyday object.
It really does. And this breakdown raises that important question, doesn't it? How much do we really understand about the true cost of material, the energy, the human effort, the logistics embedded in the common goods we use every day? This mug example is a fantastic illustration of that whole complex chain. Even for something seemingly basic, it really highlights the value built into things long before we ever see them.
Understanding that whole process, how things are made and what drives the cost, leads right into the next logical step. How do people actually choose which specific ceramic or wax to use for a particular product? This is crucial for designers, engineers, artists, anyone creating something new. What are the key things they need to look at?
The source lays out 4 absolutely critical specifications, kind of like a checklist.
Yeah.
Number 1, and it dictates everything else, is the intended use. What is this thing actually going to do? What job does it have? What environment will it be in? A ceramic for a dental implant has vastly different needs than one for a roof tile.
Right. Function first.
Absolutely. Second, the mechanical properties. This covers things like strength, how much force can it take, hardness, resisting scratches or wear, and porosity. Does it soak up liquid? These determine how durable it will be and if it's suitable for holding liquids or bearing weight.
Makes sense.
Third, thermal properties. Especially important if heat is involved. What's its melting point? How well does it conduct heat? Do you need an insulator or something that transfers heat well? And fourth, chemical properties. How well does it resist corrosion, acids, bases, other chemicals? This determines its lifespan in different environments, whether it's industrial or just household use. Those 4 areas used, mechanical, thermal, chemical, pretty much cover the essential performance requirements you need to define before picking a material.
That's a really clear framework.
Okay.
And if you're looking to actually buy these materials, especially on a larger scale, who are the big players? The source gives some examples.
It does. For ceramic materials, it lists some names you'll likely recognize. American Standard and Kohler, huge in bathrooms, sinks, toilets.
Definitely know those.
Mohawk Industries and Johnson Tiles, major players in floor and wall tiles for construction. And also DuPont, which is a massive chemical company involved in all sorts of advanced materials, including ceramics.
Okay. And for waxes?
For waxes, some interesting names. Crayola, obviously, crayons or wax, just shows the consumer side. But then you have industrial giants. ExxonMobil, an energy company, makes sense with paraffin. BASF and Ashland Global Holdings. These are huge chemical companies supplying waxes for everything imaginable, industrial lubricants, coatings for packaging, adhesives, you name it. It really underscores that these materials are part of massive global supply chains, operating on an industrial scale way beyond just candles or crayons. Hashtag shagtag outro.
Wow. We have covered a lot of ground today, haven't we? I mean, from those tiny ceramic figures made, almost 30,000 years ago, all the way to engineered glass ceramics in our kitchens.
Yeah, quite the journey.
And with waxes, too. From ancient tallow lamps to modern, sustainable soy wax candles chosen for their scent. What really comes through is that ceramics and waxes, even though they're so different chemically, are just incredibly versatile, absolutely fundamental materials. We rely on them for so much durability, function, beauty, and the things that make up our homes, run our industries, even push the boundaries of technology. We've looked at their history, their science, how they're used, even broke down the cost of a single mug.
Exactly. And I think digging into that, understanding the basic nature of these materials, how they developed over millennia, their specific properties, it really can deepen our appreciation for the engineered world all around us. It sort of encourages you to look at ordinary objects differently, doesn't it?
It really does.
You see a mug or a candle, and maybe now you see a bit of that history, that science, that manufacturing process behind it. It's a reminder that even the simplest things often have these really quite profound stories of human ingenuity and need embedded within them. So maybe the next time you pick up that ceramic mug or light a candle, just take a second and think about it, and maybe ponder this. Where do you think the next big material innovation might come from? How could combining properties or finding new applications for materials like these, building on this long legacy, change your daily life in ways we haven't even thought of yet? What's the next chapter for materials like ceramics and waxes?